All right, boys and girls, welcome back to the drive-through for a special remix of 10-4, audio included this time. Sponsored by the deli. Hungry? Stop by the deli. Get yourself a bologna sandwich on Wonder Bread with French's mustard, a little ghetto sandwich. All right, this is 10-4, secants and tangents, okay? You'll recognize that word tangent from SOHCAHTOA. Secant's another word that's closely related with SOHCAHTOA. We're going to have a bunch of definitions and a couple theorems today, and then we'll finish with a kind of a movement into tomorrow's video, for which I'll give you some help on two really, really challenging types of problems. So you'll find that this is a really challenging section. So let's start out with some definitions. A secant is a line that intersects a circle at exactly 2 points. Another way to think about a secant line is that it contains a chord. A tangent is a line that intersects a circle at exactly 1 point. This point where the tangent line touches the circle is called the point of tangency. So we'll draw a couple lines. Let me move that blue one down to the bottom and change colors here. Can you identify which of these lines is a secant and which one is a tangent? The blue line is, well, that's the one that contains a chord. So the blue line is a secant line. The green line is the tangent line. Okay, so now that we've kind of got tangents and secants established as vocabulary words, let's read two theorems, okay, and mark these down. Feel free to pause the video if you need. A tangent line is perpendicular to the radius drawn to the point of contact, or to the point of tangency, okay? The converse to that is also true. So if a line is perpendicular to the radius at the outer endpoint of the radius, then that line is tangent to the circle. So what I've done here is I've constructed a blue line and a pink radius. And if we know that that blue line is tangent at that point right there, the point of tangency, then we know that the blue line is perpendicular to the pink line. The converse of that is also true. So if we know that the pink line is perpendicular to the blue line, the pink segment, I should say, is perpendicular to the blue line, then we know that blue line is a tangent line. Now you might be wondering, like, is this tangent? Is this the same thing as opposite over adjacent? Not exactly, but kind of. You can see that if I drew a right triangle there, the tangent line and the radius would form, well, the tangent segment and the radius would form our tangent ratio. But don't worry about it. I just didn't know if you were that confused or interested about that. Okay, so as we move on a little bit, this is what I call the ice cream cone theorem. Okay, if two tangent segments are drawn to a circle from an external point, then those two segments must be congruent. So here we've got a circle with an external point. If I draw a line that's perfectly tangent, and I should say a segment, and another segment that's perfectly tangent, you'll find that those two blue segments are certainly congruent to each other. Okay, maybe you can kind of see how we would prove that. We would draw our points of tangency. We know that they're perpendicular at that point, and you can maybe see your kite there. Here I'll demonstrate why we call it the ice cream cone theorem. You get it? I hope so. Okay, finishing up the video. here are two different vocabulary words. So we've got internally tangent circles, and we have externally tangent circles. Internally tangent circles are circles that share a point of tangency, whereas one circle or more than one circle lies completely on the interior of another circle. So there you have three circles that are internally tangent to each other. They all share the same point of tangency. Externally tangent circles share one point and lie completely on the outside of each other. So those circles there would be examples of externally tangent circles. Okay, now students get these concepts confused with what we just learned all the time. Not common internal tangent circles, but now let me just talk about common internal tangents and common external tangents. We're just going to use one picture for both of these things. So we'll start out with any two circles. You can see here I've drawn one line that's tangent to both circles in pink, trying to use a straight edge to do this. There's another tangent to both circles. Those are called common external tangents. Common external tangents. Okay? Notice that the common external tangents do not intersect in between the two circles. Next, we will write two examples or two common internal tangents. So we'll switch our colors up. Do the best we can. This thing is not synced very well right now, so it's really hard for me to be exact, but consider that blue line to be a tangent line-ish. All right, let's try again. Okay, notice when we form the other common tangent, they will intersect with each other in between the circles. And that relationship between those blue lines, they are common internal tangents. So that's really all of the theorems and definitions that go along with today's lecture. Okay, there are going to be some of the most challenging homework questions, but they're to the right student, they're enjoyable. They're not long and annoying like a proof. They're kind of tricky and process-based algebra questions. So I don't want to say tricky, just in the sense that as you do them, you start to get good at them, and the challenge is something that I think you'll really understand and appreciate. So that's the end of my remix. Have a wonderful afternoon. We'll see you tomorrow for some more help. Boom!